nicely with Tarun's talk. There is, again, some overlap, but we're looking at a fairly different angle on seeing some of this monitored physics in circuits with measurements through space-time duality on unitary circuits. It's based on these two references, and also this is Tarun's reference. And then if I have time at the end, I also want to cover another interesting recent development. But so again, Tarun gave a very nice overview of the topic, but let me just quickly repeat some just for the sake of making a self-contained talk in case people catch up with the recording. So this field of monitored circuits arises when one tries to incorporate in many-body dynamics both fundamental processes that we learn about in our first encounter with quantum mechanics. So we learned that a system evolves unitarily under a Schrödinger equation when we are not looking at it. But when we do look at it, then we know that it evolves in a discontinuous manner, and the wave function collapses onto some subspace that's compatible with the outcome of our measurement, right? Maybe this is not a fundamental theory, maybe there is a more deeper unified theory, but certainly for the practical standpoint, this is how things seem to work. So the idea is to merge both processes in a genuine many-body dynamics and have our measurements be not simply probes of the dynamics, but actually active agents, and see what happens from the interplay of both processes. And this is a set of questions that makes a lot of sense, recently from the experimental standpoint, because of the advent of these quantum computing platforms, in particular these NISQ or noisy intermediate scale quantum simulators or processors, which are allowing us to execute operations that are very much like this schematic circuit here, consist of both unitary gates and also projective measurements on individual qubits. So these type of questions that would not have made a lot of sense a couple of decades ago now is actually of practical relevance and experimental accessible to some extent. So the lightning fast overview of these phase diagrams for these monitored circuits goes like this. Imagine we have a circuit with a brickwork array of gates, which sets a clock. There is a unit of time. And then we can have a certain rate of projective measurements. So every qubit, after being acted upon by the unitary component, can may or may not be measured with probability p. And so as one tunes this value of p, there are two extreme points that are easy to understand. One is p equals to 1, which means we are measuring every single qubit at every time step. And this, in some sense, Zeno localizes our wave function into the computational basis and doesn't let it develop any amount of entanglement past an order 1 bit amount. The other easy point is on the opposite end, p equals to 0, which means that there's no monitoring in the system. It's simply a random unitary circuit which, absent any constraints, achieves a thermal volume loss state at late times. And the surprising result of these papers from 3 years ago was that these two trivial points actually extend to phases that occupy this entire line and meet up at a critical point, at a finite value of this measurement rate. So the one problem with this physics, or with at least realizing this experimentally, has to do with the intrinsic quantum randomness of measurement outcomes. So we perform a measurement, and there's no way that we know of to influence the outcome. It's going to be sampled randomly through the Born rule from the wave function, right, in an unpredictable and random manner. So this is a problem because all of the interesting phase structure here in the entanglement of the state at late times doesn't show up in the average density matrix that one obtains from these circuits, but only shows up in individual pure states of the late time dynamics. So imagine, again, we have this cartoon circuit here with 3 measurements. Each one is, say, measuring the sigma z matrix and might get spin up or spin down outcome. Each one of these outcomes actually bifurcates the evolution of our state into 2 potentially completely different many-body wave functions. So because of the wave function collapse, the effect of this projective measurement is actually not local, but actually globally, can globally affect and collapse the wave function. So each time one of these measurements happen, our ensemble of states duplicates. And so as you can see, after a certain number of measurements in our system, we have an exponentially big ensemble of these pure states to look at. And
Matteo,
yes,
is there any particular reason of the Z measurement? I think Tarun also chooses the Z, so I was.
not at all. It's in terms of, we like to think with a computational basis, but any local measurement would broadly give you the same
Yeah,
phenomenology.
thank you.
Yeah. So yes, so all the, say you want to measure correlations or entanglement on a given wave function, you need to produce many, many copies of it. Because if you just, if you perform your measurement on whichever wave function you get without conditioning on the outcomes, then you're effectively probing this average density matrix, which is not good. It gets you this incoherent mixture at late times and doesn't show any of this phase structure. So basically, we need to produce one of these, choose any one of them and produce it many, many times, which comes with this catastrophic overhead that is exponential, not only in the system size, but also in the depth of the circuit. So to give you some intuition, this is worse than classical simulation of a quantum evolution, right? So it's a very bad and impractical overhead. Something needs to be done to make this experimentally viable, right? So the idea that we follow is to actually use space-time duality, which I'm sure we're all familiar with in this particular workshop, but was introduced with different goals in mind. So on the one hand, looking at these dual unitary models where you have a unitary evolution and its space-time dual is also unitary, this affords you a great deal of analytical control and lets you address questions in quantum chaos and thermalization, etc. And on the other hand, looking at circuits that aren't dual unitary, so circuits whose space-time dual is some non-unitary object, can also be useful for an array of questions ranging from local relaxation of information, this influence matrix works by Alessio and Dima and others, and also MBL, like this works by John Chocker and others. So the angle there is, can we use these non-unitary transfer matrix type objects to learn about the original unitary evolution, certain features of it, thermalization or localization, etc. And our angle is somewhat opposite. So can we, by connecting two dual objects, a unitary one and a non-unitary one, can we actually learn things about the non-unitary evolution by borrowing knowledge from the unitary one? So to give you a pictorial representation, imagine we have the space of all possible circuits, including all kinds of unitary and non-unitary elements. And then in this space, we have a submanifold of unitary circuits. So this red line here, which is simply obtained by not using any measurements or any non-unitary process. So acting with space-time duality gets us from this manifold to this other blue one, which is simply consists of all the circuits that may or may not be unitary but have a unitary dual. So this manifold intersects the other one and gives us dual unitary models. But it also has, more generally, contains all the other models that are, embedded in this space of unitary measurement type evolutions. And so the idea is that these circuits in the blue manifold, if you will, give us a set of analytically tractable and experimentally advantageous monitored circuits that it makes sense to study from both the theory and the experiment angle. Okay, so more in detail, we know that space-time duality microscopically works out by taking a certain quantum gate and exchanging the role of exchanging space and time, and more in particular exchanging indices of this gate. So instead of considering these two bottom qubits as inputs and these two top qubits as outputs, we can reshuffle our indices and have an effective dual gate whose inputs are on the left and outputs are on the right. And because we're permuting these indices in some way, we are genetically breaking unitarity. And this gets us an object that if we perform a polar decomposition on it, we can view it as the composition of a different unitary and some positive Hermitian matrix, which you can think of as a generalized projector. So it's more technically could be seen as an element of a POVM, which is a generalized quantum measurement. So functionally, it's like doing a measurement, potentially a weak measurement, but one that has a deterministic outcome. So there's none of the randomness that we were struggling with earlier. And we get some kind of effective monitoring that we might want to use in order to study monitored entanglement dynamics without the associated overhead of post-selection, right? So that's the idea, and it's not at all obvious that this should work at this stage because one has to specify these circuits in reality. And but to give you a little bit of a feel of how this would work, we can start from the simplest example. Take our unitary matrix to be the identity, so 2-qubit identity matrix diagrammatically can be represented as having 2 inputs on the bottom. Each one has its own word line, and the word lines simply evolve into the future and come out at the end without having interacted with each other at all. So if we dualize this, that means looking at this kind of diagram on the right. And you can see that, so these lines here are simply forcing the 2 states at the 2 ends to be the same. So this is obvious on the left, where we are simply stating that the input state should be the same as the output state, because this is the identity. On the right-hand side here, this line is forcing our 2 input qubits to be in the same state, but it's not telling us which one that should be. So this amounts to projecting onto this particular bell pair state, so up, up, plus, down, down. So you don't care which state the 2 input qubits have, except that they have to be the same, right? So this is much like performing a Bell measurement, except the outcome is predetermined. You don't get to randomly sample from the 4 possible Bell states, 0, 0 plus or minus 1, 1, 0, 1 plus or minus 1, 0. You always get this one. So this is the kind of idea behind what I just said about attempting to alleviate the overhead of random measurements by using space-time duality. Okay, so in a practical sense, how can this be? How can this be used in practice? So in a digital quantum simulator setting, how can this be realized? Okay. And the idea that we propose is based on quantum teleportation. So quantum teleportation as a single qubit protocol is shown here on the bottom. And the setup is one where we have 2 agents. Let's call them Alice and Bob. They have, Alice has a single qubit state psi that she wants to transfer over to Bob. And they also share entanglement as a resource. They have 1 maximally entangled Bell state. So teleportation can be accomplished if Alice measures her 2 qubits and obtains this particular Bell state. So if that happens, then her state psi actually gets teleported over to Bob's qubit. And this is kind of apparent from this diagram if you just view it as a straight line that's connecting the original input to the final output. Okay, so the idea is to dress up this protocol and make it into a many-body quantum evolution, and the overall circuit is represented here. So we have again an input state here on the bottom left, except it's now a many-body state on a one-dimensional chain of qubits that could be arbitrarily big. Then we have we aim to recover an output state on the top right, so some other ancilla qubits that we're injecting there. And we are initializing a whole set of Bell pair states on the bottom right here. Again, we have some set of ancillas in our lab, and we initialize them in these Bell pair dimers. So then here in the bulk of this circuit, we have whichever unitary evolution we choose. So some unitary U that we aim to dualize. And then the final step in the process is to eliminate all these other qubits by projecting them onto that same Bell state, up, up, plus, down, down. So this part here is where post-selection comes in. So these are measurements that you have no way of forcing. You actually have to perform and then post-select. But the advantage is that these measurements are only occurring at the boundary of the circuit and at the end of time. So this is advantageous because in number, this is a number that scales with the boundary of our space-time circuit. So, L plus T, size plus depth. as opposed to the more generic case of these monitored circuits in which there's a density of measurements across spacetime, and so the actual number of measurements scales with the product of L times T, okay? So this is a parametric reduction in this number of measurements, which results in an exponential reduction in the number of runs that one has to do to obtain a certain number of samples from this circuit. So yes, so if you realize this evolution in the lab, you actually are able to prepare, to send some input state through your circuit in this spatial direction and obtain your output on your quantum simulator at the same time, but your output state is actually related to the input state through this dual of your evolution. So you have implemented space-time duality with reasonable ingredients, 2-qubit gates, ancillas, bell pairs, and a reduced number of measurements. Okay, so that's so far as implementing this in practice. And then of course, the more interesting question from the theory standpoint is what can we gain through this idea? What kinds of entanglement phases can we realize in these circuits? So the idea to understand this, to address this question, is to aim to relate the regimes of entanglement growth in unitary dynamics that we know from developments in the approach to thermal equilibrium that we've had in the past decades, and relate all of this wealth of behaviors for the growth of entanglement in time to a similar wealth of behaviors for the scaling of entanglement in space in these dualized evolutions. So here I have a schematic line of different regimes of entanglement growth that one might have in quantum circuits, arranged roughly from the least entangling one to the most entangling one. So on the least entangling side, we have Floquet-Anderson localized circuits, whose entanglement doesn't grow past a constant. Then we may turn on weak interactions and obtain an MBL circuit whose entanglement should grow logarithmically in time. And then at some point, we have an MBL to thermal transition where entanglement growth becomes algebraic. But at first, it's bottlenecked by strong disorder and rare regions. And so it doesn't immediately grow ballistically, but it grows with this exponent alpha that varies continuously between 0 and 1 as you move further into the ergodic phase. And eventually, you cross over into a chaotic phase where the growth is ballistic. And finally, you have these dual unitary models where it's not only ballistic, but also fixed to have maximum velocity. And all of these regimes can be attained in a quantizing model shown here as one makes, for example, by setting these H fields to 0, one makes the model free. By turning them on, one makes it interacting. And then one can make the couplings clean or disorder and engineer all of these different regimes from localization to chaos. So the idea is, again, echoing part of what Tarun explained in his talk, can we dualize these phases in unitary circuits to phases in their monitored duals? And so I'm going to show a bit of a derivation of how we connect these two entanglement quantities across the duality. And the quantity that I aim to compute is this entanglement of a pure wave function that exists at this time-like boundary of a quantum circuit, okay? So we have a brickwork circuit made out of unitary gates whose unitary direction is signaled by the direction of this little arrow here. So the circuit would be unitary in the vertical direction. However, we are thinking of evolving a state sideways and recovering it at this time-like boundary here. Okay. And also we choose this bell pair initial states on the left because it's kind of technically convenient for this derivation. And it's a perfectly legitimate short-range entangled initial state that shouldn't have catastrophically special effects. So we want to compute the entanglement entropy of this final state on some subregion A and study how it scales with the size of A at late times. So we are going to make this sideways depth infinite eventually and look at the scaling of this entanglement here. So The key simplification that comes into play here is that in the limit in which this region, this complementary region A bar is taken to infinity, so we consider a finite subsystem embedded into an infinite complement, then there is an isometry between the qubits that live at this entanglement cut B and the qubits that live in A bar. So an isometry is like a unitary, but it's between a smaller space and a bigger space. So you're isometrically embedding some smaller space of states into some bigger one. But that means that no information is being lost. So all the information that makes it across the entanglement cut B, from A across this cut B, is going to come out the other side. None of it is going to wrap around and come back into region A, intuitively. So that allows you mathematically to elide the entire portion of the circuit that is above the cut B, and it gets you this kind of circuit here, which is a pure state with this bipartite structure where half of the output legs are on this time-like A surface and half are in this, or not half, but some subset are in this space-like region B. Okay. So this is a much smaller circuit, and it's helpful to analyze it in this way, but we're going to get the same answer that we would have gotten here. Okay. And now, because this is a pure state, we want to get the entropy of A, but we can choose to trace out either subsystem. It doesn't matter, because it's a pure state, the entropy of some of the qubits is going to be equal to the entropy of the complement. So we choose for convenience to trace out A instead of B, right? And doing that amounts to taking, we have to take the ket and bra product of this state, which amounts to these two layers. Top layer, that's the ket, if you will, and the bottom layer, that's the bra. And then we have to partially trace out subregion A, which means that the legs that are coming out here have to be connected together in this way. But now this has a fascinating dynamical interpretation, because this process here, if you view it dynamically along the vertical direction, corresponds to a fully depolarizing or erasure channel. So it means that whenever you have one of these loops that are sort of upwards facing, that's an identity matrix. Like that's a Kronecker delta between the input and output, or the ket and bra right there. So it's an identity matrix. And whenever you have one of these downward facing arcs, that's a tracing out of the qubit. So putting it together, this gives you this sort of trace out and sticking an identity type of operation, which is a depolarizing channel. Okay, so dynamically here we have a unitary circuit in the bulk, and this very strong thermal bath, basically, that's decohering one edge of our one-dimensional chain, and then this entropy that's injected at the edge is going to be transferred into the system and make it into this final state at B, which is going to be mixed. And so the key result here is that the entropy of this state, the mixed state of B that we obtain, actually equals the quantity that we set out to study. So we have this identity here that connects entanglement across this space-time duality. So on the left-hand side, we have this pure state obtained from the dual evolution at infinite depth, so steady state type quantity. And on the right-hand side, we have this temporal growth of entanglement in a mixed state in this dissipative unitary plus decoherence type evolution. So this is a powerful identity that lets us use various techniques that have been developed for unitary circuits in this slightly more complicated problem with a twist of decoherence here at the edge, and lets us use those methods to learn about the entanglement scaling of the dual state. Okay, with this tool in hand, we can go back to the question that we had earlier of dualizing all of these regimes of entanglement from growth in time to scaling in space, and we obtain this set of answers, which I'm going to quickly walk through. So maybe the more novel result is that these sub-ballistic scaling of entanglement here dualizes to a sub-extensive growth in space in the dual. So this is, Tarun has shown us their fractal scaling in space in this Floquet Aubrey ring model. There's a few more examples where you obtain fractal scaling in space in various free fermion systems or like Motkin chains or such, algebraically fine-tuned models. So these examples that are all in either free or somehow fine-tuned models. This model here has qualitatively different kind of structure. So it's an interacting, monitored, time-dependent evolution. So it's kind of a robust fractal scaling that is enabled by breaking unitarity, let's say, something that you don't normally find in this fashion in unitary evolution. Then the second striking result here is that there's no areal of phase here. So you notice that even the Anderson localized models whose entanglement normally wouldn't grow past the constant, upon dualization, they become logarithmic. And this is part of a more general result where by looking at that identity that I just showed, you can see how areal of phases are essentially forbidden unless one has an exact cut in the system. So again, in one of the models that Tarun showed, you can disconnect a bond and repeatedly, and that gets you an areal state at late times in the dual. But you literally have to disconnect everything. That's key. If you have generics systems where there is some probability of where there is always some probability of not actually disconnecting the bonds, then areal of phases are essentially forbidden. And then finally, we have the duals of chaotic circuits, where this ballistic growth of entanglement in time translates to this extensive scaling in space, as one might have expected. We can prove that in focusing on hard random circuits that are good toy models of chaotic dynamics that I'll go into a bit more detail in a second. We can show that the entropy density of this volume law phase equals the entanglement velocity in the unitary. So again, a manifestation of space-time duality where entanglement per unit time goes to entanglement per unit space. And then, very interestingly, we have this sublinial correction, this logarithmic correction that comes from the HT coherence, and that has a very important role in the stability of these volume law monitored phases. So I'll say a bit more about that next. But other questions about any of these other things here before I move on? Okay, if not, then let me move on to the study of these duals of chaotic circuits, which we do by looking at hard random circuits. So circuits that are brickwork arrays of 2-qubit gates that are sampled independently and identically out of the Haar measure. So the measure that's unitarily invariant on the unitary group, on 2 qubits in this case. And we can make the on-site dimension Q completely arbitrary. It doesn't have to be qubits now. So there have been developments a few years ago on analytically evaluating the entanglement growth in these circuits. And in particular, what one can do is perform the exact average of this purity quantity, so this trace of rho squared, which is related to the annealed average of the second Rayleigh entropy. So to do that, rho squared, so the density matrix rho is comprised of a ket and a bra, if you will, and then its square doubles this stack of gates, and we get 4 of these stacked gates, two gates U and 2 gates U star, and we can average this overall stack of gates over the unitary group and obtain some tensor that's analytically known, and then we can simply compose all of these tensors in space-time to get our average quantity. And the key here is that the boundary conditions are where all the where everything is happening. So we need to differentiate between qubits that are inside the region A, whose entanglement we are calculating, and qubits that are inside. So qubits that are outside the region are being traced out, which means that the two, each ket is being paired up with its own bra. So there is this kind of pairing between the 4 legs, and qubits that are inside the region are instead being, to get the square of rho, they're being paired up in this other fashion here. So these two different possibilities amount to essentially Ising spin variables. You can think of them as the up and down spins, or calling them plus and minus here. And there is this very elegant picture in which there is a domain wall between the plus and minus spins, and this evolves in time by hopping either left or right whenever it encounters a gate. So you have equal probabilities of moving one side or the other. And this gives you, by summing over all these random walks, you obtain the analytical result of the growth of entanglement in time with this analytically computable entanglement velocity given here as a function of q. So this is just background on this technique that's been developed in some of these papers from a few years back. And now we aim to apply this to our particular setup, in which instead of having entanglement between two spatial subregions in a final state of a unitary evolution, we have this different problem of a mixed state that's produced by unitary evolution in the bulk and this particular edge decoherence at one of the boundaries. Okay. So the decoherence appears again like this plus spin. It's essentially tracing out the qubit. So it behaves in the same way as the complement A bar in the previous calculation. And so here we have this entanglement domain wall that is seated exactly at the boundary of the system, and then can evolve backward in time in the same way as before, except the rules of the game are modified near the edge. So near the edge, if you choose to hop away from the edge, you're fine. You get the same 1/2 probability. But if you try to hop past the edge, then you get a penalty. So you get some amplitude that is less than a half that causes overall loss of probability. So you have a random walker that's trying to move backwards in time, but it's being partially absorbed by this boundary. And so what matters for the calculation is the survival probability of this random walker with this partially absorbing boundary condition. And there's results on this which tell you that the scaling of purity that you found earlier gets modified by appending this factor of square root of t. And so after taking a log, this gets us the entropy of V times L, which is what I promised earlier. So the entropy density is equal to the entanglement velocity. But then it also gets you this universal logarithmic correction here, which signals this state as a non-thermal volume law entangled state and has key connections to the physics of these phases as emergent quantum error correcting codes. So somehow in the canonical unitary measurement circuit, people think of it as the unitary gates are scrambling the information, forming a quantum error correcting code that prevents the measurements from reading out the information and therefore stabilizes the volume law entanglement. So there's various StatMech models to understand this quantum error correcting code, and they expect this 3/2 log L scaling for this subleading correction based on that. And indeed, that's the same thing we find, because the 1/2 that I just explained comes from this boundary condition where the system is near the edge. So it's there is an edge, then there is our system A, and then there is the complement, which is semi-infinite. And so this gives you this kind of point-to-line random walk boundary condition, which gets you this 1/2 factor. But if you choose instead a system that is in the bulk of an infinite system, you end up with a point-to-point random walk, which gets you these 3/2. So, and there is even finer evidence in some mutual information quantity that I'm not going to really explain, that suggests that these duals of chaotic circuits are actually in the same phase as more generic unitary measurement circuits in their respective volume law phase. So we have this conjecture that basically these space-time dual circuits are belong to the same universality as more general circuits in that broader space that I showed earlier, the space of unitary measurement circuits. Okay, so that's all I wanted to say about that. How am I doing on time? Do we have 10 minutes? Okay, yeah, well, I assume I do. So I'm going to, I wanted to present very briefly because I think that this audience will find it interesting, some new results on a completely different application of space-time duality, or actually some generalizations of it, to these so-called triunitary circuits. This is a paper that's been published just this last month. So the question here is, can we generalize some of the powerful results that have been obtained with dual unitary circuits? And those results, in some sense, are obtained because of the particular causal structure of these evolutions. So we know that if we have a unitarity along some matter of time, then there is some bound on, we have a causal light cone in our circuit that prevents us from finding correlations outside, in what's basically the present of our space-time point, right? We can have correlations in the future or in the past, but not outside of the light cone. Now, if we have unitarity about this second arrow of time, then in some sense the same should hold for these other wedges in space-time, right? Somehow all of space-time becomes forbidden, and the only location you can find correlations is actually at the surface of these light cones, so along these special directions. Now, this is a bit simplistic. In reality, one has to look at a tensor network contraction, but spiritually, this is the constraint that's coming from the unitarity that's placing this restriction on the correlations. And the idea that we consider is, what if we embedded more arrows of time? What if we had an evolution in 1 + 1D space-time where you had not only the unitary arrow of time as usual, but also 2 additional ones at these 60-degree directions? Well, in that case, you would have the same kind of reasoning, basically rule out the entirety of 1 + 1D space-time and restrict your correlations on these 3 directions now. So not only these light cone edges, delta x plus or minus b delta t, but also this static word line, delta x equals to 0. So you're allowed, just on grounds of unitarity and causality, to have correlations between an operator at the origin and an operator at later times, but still at the same position. Okay, this is qualitatively different from the restriction that's imposed in the dual unitary case.
Matthew, you
yes.
have approximately 3 to 5 minutes.
Yeah, okay, great. I'm going to
Thank you.
wrap up on this very quickly. So how can one do that? So in order to impose this higher symmetry on our evolution, we need 3 qubit gates. We can do it with 2 qubit gates, and so we can represent these as hexagons. So tensors with 6 legs that we can group into inputs and outputs in various ways. So conventionally, we have inputs here and outputs there, and that gets us this conventional arrow of time. But we can also group them in different ways between input and output, and we impose unitarity along all of these contractions between contiguous input and output legs. So this is something that's been studied in various contexts under various names. But a particular realization that we find is this gate set composed of controlled phase gates and 1 qubit gates, which is a big space of 31 parameters, lets us realize various regimes. But also we know that it's not complete. Like there is a 6 qubit perfect tensor that you can prove does not belong to this set. So we know that there's more. It's an interesting problem to fully characterize the entire space. But aside from that, once we have this building block, we need to build this evolution, which is invariant under this higher space-time symmetry. And the idea is to simply place these objects on vertices of a triangular lattice, which under more conventional, rectangular-looking gates has this representation here. And with this, we find various results that in some ways generalize what's known about dual unitary circuits. For example, we can compute entanglement. We find a very similar result, that is, from some class of solvable initial states, there is a maximum velocity growth of entanglement, but only up to 1/2 of the maximum density. After that, the derivation stops working. Some complications arise, and actually that corresponds to a start of some model-dependent behavior that we can analyze numerically, and you can see that looking at various gate sets going from non-interacting to strongly interacting, we have this universal maximum velocity growth up to about halfway, and then sort of the onset of some model-dependent entanglement growth behavior at later times. And then there is also a higher dimensional generalization, which turns out was also envisioned by Bruno and Pavel and Tomasz in their earlier paper, but it's very natural with this gate set because you have 6-legged objects. It's natural to arrange them as cubes. Cubes have 6 faces. You stick a tensor network leg on each face, and you can arrange these on a 3D cubic lattice. And then much the same reasoning that one can use for correlations in 1 + 1D goes through. And you find that correlations are pinned to the x, y, and z directions in this cubic lattice. except time is actually fully, it's in the 1-1-1 direction, for example. Right? It's in the middle of these three of this tetrahedron. It's the octant of space-time. And so once you project this back into two-dimensional space by taking a slice that's orthogonal to T, you get some Kagome lattice in this case, and the correlations turn out to be pinned to special directions in this two-dimensional space. So this is a rather distinct behavior because correlations are not pinned to the to the surface of a light cone in the sense of an object of codimension 1, but they're pinned to actually manifolds of dimension 1 as you go to higher dimensions. So it's a sort of subdimensional spread of information that's kind of tightly fine-tuned but kind of striking. Okay, so that's a very fast overview of this recent work. I wanted to just wrap up by recapping what I talked about, which is these monitored circuits as a new arena for actual equilibrium phases and universality, and how we can access some new regimes in these space-time duals of unitary circuits. And we can do so in a way that's experimentally motivated, that saves us exponentially many runs, and also allows us a degree of analytical control that lets us find universal aspects of these phases. Both phases that we knew, such as the volume law, non-thermal one, but also these new fractally entangled phases. And then with these unitary circuits, I think that there are interesting questions about what else can be done in this vein. How what kinds of generalizations are possible beyond this, and what other quantities can be computed. With that, I'll thank you for your attention and be happy to take any questions.
Thank you, Matthew. Thank you for the wonderful talk. So, any questions? The floor is open for the questions. Okay, so I think if there are no questions, I have. Okay, I have one question, and then you can ask.
Sure.
Yeah, you ask. Okay. And maybe same questions.
No, I was just looking at this. What are the initial states you are taking for the tri-unitary circuits? So they're solvable in what sense?
They're solvable in this sense. So this is a generalization of what Lorenzo and others had done for the dual unitary case, where you have, in this case here, we have so it's crucial to have these bell pair states that are these bonds here. And then we can interleave them with arbitrary single qubit states, doesn't matter which. This is important in the calculation because you can, if you have this kind of diagram where these two boundary conditions that refer to whether you're in or out of the entanglement region, you can simplify them backwards just on grounds of unitarity in this way. And then you're stuck here, and you need to, by imposing triunitarity, you can say that this gate gets elided, but then you need to somehow transfer the resulting identity matrix over to the next gate, and that can only be done if you have a bell pair state there. So that's what allows you to sort of destroy this network from the edges.
Okay. Nice. So it's essentially what this exact dynamics in dual unitary circuits like that. The class of.
Yes.
Okay. So is it like if you impose now, so in the tri-unitary case, you will have 10 possible partitions, right? So out of 10 possible partitions, you're assuming unitarity in 3. So if you assume more than 3, for example, there will exist tripartite gates. And in fact, for qubits also, which will be unitary along more than 3 directions also. Do you think that there will be some simplification in the entanglement dynamics and all?
Right. So at this stage, you are really only encountering connections of contiguous legs. So I don't think that would be the case. In particular, we have done these numerics also incorporating the perfect tensor on qubits.
Oh, okay.
And you can look at it, and if you look very closely, you'll see that it's not really, it's some non-universal numbers here. It's not exactly continuing on a straight line. So presumably there's no further analytical simplification there, even in the perfect case.
Okay, interesting. Actually, I didn't see that you have the numerical result for perfect answer also.
Yeah,
okay.
We just thought we'd check.
Matteo, I have two.
Yeah,
Thanks,
please proceed, Arvinda. Yeah.
Matteo, I have
I-
two questions.
I'm sorry.
One thing you might have already answered, but I just wanted to know. So, in using the triunitary dynamics, do you see any specific difference between the entanglement dynamics of biunitary versus triunitary? Biunitary means the dual unitary is acting on two parties. So, that's what I use when I use the biunitary.
So you mean dual unitary acting on what?
On only two sides, the standard
Okay.
unitaries.
Sure.
So
Okay. Yes.
versus the triunitary. So that's what I mean.
Right. So broadly speaking, both give you this strongly chaotic maximum velocity growth. There is this bit of a difference on what class of states exactly can you solve for both. And in this case, it appears that the solvability kind of stops halfway to the maximum entanglement. Whereas in the dual unitary or biunitary case, you can extend it all the way to maximum entropy, and then you have a maximally mixed density matrix, and that's it. Here, somehow you can kind of think of this of these systems as ladders that combine a dual unitary chain with some additional chain, and when you have this interaction equals to 0, you have no coupling between those two chains. So there is a dual unitary chain that's contributing all the entanglement, and then there is a decoupled set of qubits that are doing nothing, and so the entanglement stops there. And then you can controllably couple in those other qubits, and that's what gives you the other half of the entanglement, but somehow that doesn't follow the same maximum velocity growth. That makes sense.
Yes, thank you. And second question is there a Hamiltonian characterization for triunitary?
Hamiltonian in what sense? You mean a model that's a time-dependent
Okay.
Hamiltonian?
So means if it is in a dual unitary, you have sigma x, pi by 4, pi by 4 if you, and then you have the full Hamilton. That's what I meant by when
I
Hamiltonian.
mean, I think he's asking for trottilization of Hamiltonian.
Right.
Yeah,
So we certainly don't have a full answer to that. The most we've got is this kind of this gate set here. You could write that as a Hamiltonian. It's not a particularly elegant one because of there's just all of there's
I think in their paper there is some Kickard-Ising model realization.
yes,
also.
you exactly you can realize
Sublattice
that.
and lattice.
That's along the lines of what I was saying earlier about you can have two subchain, you can have like a ladder type system, and then you can write a Kickard-Ising realization, but that requires you at least 4 steps. It's not as simple as Tomasz's two-step Kickard-Ising.
Yeah, I think you have some non-trivial local sandwiched in between these entanglement where you apply swap gate between 1 and 3, and then you have local gates in between. Is a non-trivial than in the dual unitary gates.
Yeah.
Okay.
Can I ask last question?
Yeah. The last
Yeah.
question. Okay, thanks.
So thanks very much for the very nice talk. So I have a curiosity. So I like very much your construction to reduce the number of post-selection measurements.
Mm-hmm.
So I was wondering whether, one could imagine or dream that for a special class of circuits, instead of doing post-selection, maybe you could have some LOCC at the end, some classical communication. Of course, that the circuits must be fine-tuned. So is it something? So it looks very difficult, but have you thought about this? Is there a chance that for some very fine-tuned models, this could be done?
Right. Now that's a great question because that would ultimately let you do, like, that would be much, even exponentially more efficient than this. So somehow, if you want to address that with LOCC, you want an efficiently solvable decoding problem for these outcomes. So let's say you do these measurements.
Yeah. So like if the you mentioned the transverse unitaries are Cliffords, then you could do this deterministically, essentially. Of course, these are
exactly.
the wrong direction, but yeah.
Yeah, no, exactly. You want an efficiently solvable decoding problem so that if you get an outcome that doesn't match the one you got before, you can do some classical communication and computation, fix it. That's, yeah, as far as I know, it would be only, free fermions, Clifford evolutions, things of that sort, but it would be.
Yeah, but even Clifford would
certainly
be
interesting to
interesting. I
find
mean,
more.
I think even Clifford would be interesting to because even, I mean, for unitary Clifford dynamics, it's not obvious to me that this could be done in general.
Well, I mean, you can always. So I guess it depends on what constraints you're placing on the classical component, but you can certainly, given an outcome, you can work out in polynomial time correcting Clifford unitary on the whole system that you can then apply. So it depends. Are you allowed in your, like, are you envisioning being allowed to do a unitary correction at the end, or do you want to just do classical post-processing?
Yeah. No, but here I'm just, I mean, maybe I'm wrong, but I meant if you take the Bell measurements and this projection to a product of Pauli's, right, not the identities, then you would like to pull them through at the end of the circuit and then correct them.
Mm-hmm. Yeah.
But then it seems to me this you cannot do, like, if these use are Cliffords in the correct direction, it's not clear to me that you can pull them through in the space-time direction. Sorry, in the space-light direction. But maybe we can discuss this later.
Yeah, we can discuss offline, but I think it should be possible. But yeah.
Okay, let me conclude. Thank Matthew for
Thank you very much.
beautiful talk. And I request all the participants to just
Thank you very
spare
much.
5 minutes of this concluding session